Hello and welcome to another Rust Linz Meetup. Stefan, so nice to see you.
Nice to see you again, Rainer. Hi.
Hi. Wow, this was an interesting month, wasn't it?
Yeah. So, wow, it's already end of October. That came
Absolutely,
fast.
absolutely. For those of you who visit us regularly, we had a Rust Meetup at the beginning of September, and we didn't want to leave October without the Rust Meetup. But it still was 1.5 months since the last Rust Linz Meetup, and the reason were a lot of conferences, very very exciting conferences. I had the honor to speak at multiple conferences, also talking about Rust and WebAssembly. And Stefan, I think I know one of your conference highlights. Wasn't it the
Yeah.
Eurorust conference?
Yeah. So exactly. So I've been at Eurorust mid of October. So it was on October 13, October 14 in Berlin. I was there on site and in person. You had the possibility to join on site or join virtually. There were 250 people in the room, which was tremendous. So I didn't expect so many people. And it was really good to see so many Rustaceans in one spot. It was completely sold out. They had, I guess, an equal amount of tickets sold online. So you were able to join virtually. And it was definitely one of my conference highlights this year. First of all, it was my first in-person conference after a very long time. So this is already something notable. But it was also good to earth yourself with the Rust community of Europe, because basically everybody was there. So people from all over Europe came. I had the chance to see so many Rust Linz speakers finally in person and have a little chat with them.
Yeah.
It was so great. And I didn't even manage to talk to all of them. So I was just there for 1.5 days. I had to leave early. And I tried to speak with as many as possible, and I still guess I missed half or so. And with those who I spoke, it was great to talk about, life, Rust, and everything, and it really paid off. So the hallway track was very important, but so were the talks on stage. So I assume that the organizers will put up the talks online within the next couple of weeks or so. A really great lineup with lots of interesting talks, and definitely something to check out. And as for myself, I'm definitely going to be there next year as well. So this will be my staple conference from now, because I had so much fun, and it was really, really nice to be there.
Very nice to hear you. I'm a little bit jealous. I had the chance and honor to do a talk virtually. I wasn't able to travel there, but I can tell you the experience as a speaker doing a virtual talk there was also amazing. People who organized it were super professional. It was a very nice experience. Even if you were a remote speaker, I immediately felt myself at home. They organized the Q&A sessions in a very, very nice way. So a big clap of hands for the organizers. It definitely was one of the conference highlights regarding Rust this year. Yeah, absolutely.
So it was very thoughtful, actually, that they included a Q&A session for the virtual attendees. So they felt more included in what's happening on stage. Because the worst thing that you can have is that everybody runs into the hallway track, the room is empty, and the people virtually just wait for the next thing to start. And so they were included, they were part of the discussion, part of everything that has happened here, and this was really, really nice. And you could feel all those tiny details throughout the entire conference. The food was great, the organization was great. They put up all those tables so that you were able to quickly go into a chat with somebody, and that you mingled, that you exchange with a lot of people. And from that on, it was really meant for the community, and really something that invited you to celebrate your hobby and the tech that you love. So I couldn't speak higher of your Rust. It was really a great experience.
Absolutely. It fulfilled all the promises, and it was really a great thing. So today, speaking of great things, we also have two great speakers here, and we love to have them here. One is a second time speaker can I say it this way? He is here for the second time here at Rust Linz. Matthias will do a session and Timo will do a session, and we are very much looking forward to that. Let's quickly start the evening with a round of community news. That's a tradition here at Rust Linz Meetup. As you all know, Rust Linz is brought to you by the Coding Club Linz, which is a community of passionate coders. We do multiple things, and Rust Linz is one of those communities that we maintain and try to keep alive and well and so on. Yeah, we started at 5:30, of course, and here are our speakers today. Matthias will tell us about hypervisor with Rust, and Diemo will tell us about a cellular automaton with Rust and Bevy. So I think we have two very important and interesting sessions coming up today. Matthias will go first and Timo will follow afterwards. The first presentation will end at approximately 6:30-ish, something like this, plus minus 10 minutes. And then we'll have the second presentation, and we're looking forward to both of them very much.
I'm excited to both of them. If I quickly might interrupt, because
absolutely do so.
I was able to speak to Matthias at one of the recent JavaScript meetups that you had, and the stuff that he's doing that is really, really great, and I really look forward to that. Also because I need to understand how to target hypervisors with Rust. So this is something that helps me in my daily work.
Very good.
That is. And I'm also happy that Diemo is joining, because Diemo reached out to us. He's organizing Rust Rostock. It's a lovely community on Discord, and he's doing regular meetups there where he invites speakers from the European Rust community in a very inclusive manner. So you are in a Zoom chat. People turn on the cameras, they interact with you while you're talking, which is a really lovely way to connect even over distances. So I think he does a great work with the meetup, and I think it's great that I was able to speak at his meetup, and now he's coming back to Rust Linz. So I think this is fantastic, and I'm really looking forward to welcome him on stage.
Very nice, very nice. Speaking of community, if you want to keep in touch with us, you can use our Discord server. It's not a high traffic Discord server. Don't worry, you will not be flooded with messages, but it is a great way to keep in touch when it comes around new Rust meetup. Maybe we can announce speakers or look for speakers, or you can make suggestions and things like that. So we invite you very much to our Discord server. Here is the link, and I will also we will also post it in the YouTube chat so that you can just click on the link if you're interested to join. Now, around communities, what is going on currently in Linz? Of course, we have to mention our very own Coder Dojo Linz, which is a programming club for kids. The next meeting is, as always, on Friday, 28th of October, tomorrow. And tomorrow will be a real Coder Dojo day for me, Stefan. I will do 4.5 hours together with approximately 60 to 70 kids, because we currently have vacation time here in Austria. And together with the local community, we organized digital holidays for kids, so they can join. They can join from at home. They can go in their school together with their teachers, and we will do 4.5 hours of Scratch tomorrow morning. And in the afternoon, we are looking forward to multiple workshops with web development and again Scratch and things like that. Just check out linz.coderdojo.net if you are a young coder, or if you have kids or maybe nieces, nephews, whoever. We welcome everybody who would like to learn how to code. That's our Coder Dojo Linz. Next one, female coders. Our friends at Female Coders, for girls and women who would like to start with coding or deepen their relationship with the coding community. They all are invited to the meetups, and I see I have made a mistake here on my slide. It says the hackathon for women and girls. This is a copy and paste mistake. This is not a hackathon. This is a regular meetup that's going on the 16th of November. Sorry for my copy and paste error. But however, just check out their website, female-coders.at, and there you find all the details without typos or copy-paste mistakes that I do. Next one, Cloud Native Meetup. The next Cloud Native Meetup will happen in November. 22nd of November is the next date, and here you see the link. If you are interested and you would like to check what the topics will be, there you can find more things. And that's essentially what I found out what's going on regarding befriended communities here in and around Linz. And with that, I think we used exactly the planned 10 minutes. That is exactly in time. So let's get rid of my screen here and let's invite Matthias on the stage. Hello, Matthias. Hi.
Hello, thanks for the introduction.
Yeah, thank you for being here. We love to have you for a second time here at the Rust Linz Meetup. Matthias, I know the answer, but still, I'm going to ask you the same question that I ask all our speakers at the beginning. Where are you broadcasting from? You are a local, right?
Austria, yeah.
Yeah, very nice, very nice. Yeah, we are looking forward to your talk. If you want, you can share your screen and we can bring it up and make sure that technical wise everything works properly. I already see your screen. Let me try it. Yes, and here we are. We can see it. It works flawlessly. So, Matthias, are you ready?
I'm ready.
Very, very well. We are looking forward to your talk. The stage is yours. We are looking forward to learn a lot about hypervisors and Rust.
Thanks. All right. Yeah. As Rainer already said, my talk is about writing a hypervisor with Rust. And so a little about me, and I'm currently studying computer science at the JKU, and I've been using Rust since like 2020, and I really fell into love with it. And I'm also really interested in reverse engineering and game hacking, and that's how this project got started. So let's take a look what exactly a hypervisor is. And Wikipedia defines it as a software that runs virtual machines. And there's actually a distinction between two types. A type 1 that runs directly on the hardware, which means it's a lot more effort to implement because you need to do everything on your own. And then there's also a type 2 hypervisor, which runs on the operating system. So there you don't have to do everything on your own. You can use the operating system to allocate virtual memory or physical memory. And it's a lot easier, but still a little complicated. So where are hypervisors used? What can you use them for? And one of the most common use cases is just virtual machines to run another operating system on your already running operating system. And examples for this are VMware, VirtualBox, KVM. I'm sure all of you have used it before. Another really powerful example is serverless computing. So, for example, running functions, so functions as a service on a server. And one really popular example is Amazon Firecracker, which uses Rust and is built on top of KVM. This is a Linux kernel module and handles all the hypervisor stuff. And for example, they don't have virtual machines. They call them micro VMs. And with that, they can restrict the resources they have access to. So for example, you can say this function should only access 120 megabytes of memory, or should only use up to 2 virtual CPUs. And this is really powerful because you don't just want some random guy that uploaded a function to access the entire memory or entire system. So it's really good that there's some security built in. And that's exactly what hypervisors are used for. So another example is antivirus. So with a hypervisor, so it's a hardware feature supported by the CPU. And because of that, you have a lot more control over the system. And the antivirus can effectively use it to find if a program is doing something weird, but also they can protect against it. They can protect some resources, some memory, or do some other stuff. And one example for an antivirus is the Windows virtualization-based security. And there they have code integrity checks, also protection against direct memory attacks. And it's very hard to circumvent because they are using a hypervisor. And another really cool example is fuzzing. So in fuzzing, the goal is to find states of the program that make it crash. And there you need to trace over all the instructions and also pause at certain instructions. And with a hypervisor, you can do that. And on top of that, you can even pause at a certain point and resume at another point. This is really powerful. And I really recommend checking out Gemozo Labs GitHub repository. He has a ton of really interesting projects, also written in Rust. And then there's also the bad side. You can also use it for malware or cheats. Just like the antivirus can use it to have more power for the good, bad people can use it to gain more power and to hide from the antivirus or anti-cheat. Because everything has to rely on something. Usually it's about the operating system, but they also have to rely on the hardware. So how would they know that they're running inside a virtual machine? There's some ways, some timing attacks. I'll come back to that later, but you can still do it and make it seem like they're running on a real system when they're not. So why would you write your own hypervisor? And for me, it's a lot about just the challenge. And it's a really challenging and also rewarding project. And I also wanted to learn more about the details about CPUs and like how everything works. And since I'm coming from a game hacking and security background, I was also interested in figuring out if I could actually bypass the anti-cheat. And yeah. So what exactly can you do with a hypervisor? And the answer is pretty much everything. You have control over the entire system. You can intercept instructions or memory accesses. So you can do whatever you want. So let's take a look at some parts that are involved when you're writing a hypervisor. So one of the most powerful parts is a nested page table. Or in this case, it's just a regular page table. You have a virtual address, and it goes through all the page tables, and at the end, you have the physical address. And with a hypervisor, you can have two of those. And that's called a nested page table on AMD. So if you're inside a virtual machine, you think you have, let's say, 4 GB of memory, and this virtual memory is resolved to physical memory. But because the virtual machine thinks it only has 4 GB, but in fact, on the actual host, this 4 GB is resolved again to the real machine memory. And there you can do some really interesting things like only setting certain pages to read, so no write access. And that's also what virtualization-based security does. It's really powerful. Another part of a hypervisor is an MSR bitmap. So MSR stands for Model Specific Register. And they basically allow you to read certain data from the CPU or change the behavior. And with this bitmap, you can essentially intercept those requests. So you can read an MSR, also write to one. And with a hypervisor, you can intercept those. And when intercepted, a virtual machine exit, a short VM exit, will occur. And you can imagine it somewhat like an interrupt, which just calls a callback in the hypervisor. Then the VM exit will be handled and returns to the original location where it occurred. And another part of a hypervisor is the virtual machine control plug. And it basically consists of two things: the safe area and the control area. And the safe area contains all the information about a virtual machine. So the registers, the segments, and also some debug fields. So if you pause the virtual machine, all the information is written to this struct. So you can pause it, do some other stuff, and come back later and resume it at this point. And the other part is the control area, where you can, as the name says, control certain behavior. So you can specify what you want to intercept. For example, the RDTSC instruction, which reads the timestamp counter, also the CPU ID, also read or write to the CR, the control registers, and a ton of other instructions. You can also enable the nested paging, which we saw before with the nested page table. Also set the next instruction pointer and other things. And because modern CPUs have multiple cores, you need to create this struct, the vCPU data, for each core. And each core has a guest VMCB, virtual machine control block, and a host VMCB. And then also we have a pointer to the shared data. So we don't want an MSR bitmap, a nested page table, for each core. We could, but there's not really a use case for that. So we just have a shared data for that. So let's take a look at the implementation. And for that, I'm going to take a look at how you can virtualize a single CPU. So let's switch to the code. Okay. So I have a hypervisor struct, and it basically just consists of all the CPU cores you have. And this is the vCPU struct. And when you call the virtualize method, we just iterate over all the processors you have. And then we use the Windows API to switch the execution to a specific processor, because we really have to make sure that we're not virtualizing the same CPU core, I just call it processor, twice. That's gonna fail horribly. And we just call the virtualize method on the processor struct, on the vCPU struct. So let's take a look at it, what it does there. So we pass the shared data, and then we create the context. And this context is really important that it's at this place. I'll come back to that later. The context just has all the registers and also the instruction pointer. And then we make a check if this CPU core has already been virtualized. Because as I said, we don't want to virtualize it twice. And you can do that with an atomic, and yeah, it's not really important. If it has not been virtualized, we virtualize it. So we set the flag, we do some initialization, and then we create the vCPU data. We also create our own stack, and we launch the VM with some manual assembly. I'm not gonna go through it, that's way out of scope. And then we launch it. And the important thing is, we created the context. And when we launch the VM, it will resume execution at this context. So we launch it, and then we're suddenly back here. Then we check again. Is this CPU core already virtualized? We already set the flag, so it is. So now we're not virtualizing it again. We just return true. And that's done for every CPU core. And yeah. In the launch script, we just use the VM run, and that's running until we get a VM exit. So that's how you virtualize a single CPU or multiple. It's effectively the same for multiple cores. So I mentioned the term VM exit, and it's one of the most important things you need when interacting with the guest. So we have a VM exit handler, which is called from our custom assembly. You can find it here, and that's not important. The important thing is we get the vCPU data and the guest registers. So the VM exit is again called for a specific core, and there we need to do some initialization. That's not important. And then we can, with the vCPU data, we can access the guest virtual machine control block, VMCB. And there in the control area, there's the exit code. So if we got a VM exit and our callback has been called, we want to know which VM exit it was. So for example, did someone try to read the timestamp counter? Or did a nested page fault occur? Or did somebody try to execute the CPU ID instruction? Or did someone try to read an MSR or write to one? So there's a ton of options. And I basically programmed it that you can specify your own handler. And I can take a look. Yeah. So one example for a handler, I mentioned it before, you can do a timing attack to detect if your code is running inside a virtual machine or running under a hypervisor. And one of those ways is to execute the RDTSC instruction. So we disabled interrupts because we want to make sure it's not, it's correct. And then we execute it 1,000 times or a little more. And we execute the RDTSC instruction. And remember, now a VMExit happens. So we jump to the VMExit handler. The VMExit handler executes some code, and then it jumps back. And this is the first tick. So RDTSC returns the CPU in cycles, and every time the CPU does some work, it's incremented. So when we do the second RDTSC, we read the cycles again, and we take the difference. We're gonna notice a difference because we have been executing the VMExit handler code. And on a normal system, it's pretty much always between 25 and 500 cycles. So this is just a heuristic, but in 99.999% of cases, it's always this. So how could we get around that? And I already showed you, let me switch back. We can check if there's a VMExit for an RDTSC. So let me show you an implementation that gets around that. So this is the handle RDTSC, and it's called whenever, so it's called here. And there first of all, we get the real timestamp. And we also save the previous timestamp, and we take a difference. And so so the first one is just 0, but then we save it. And then for the second one, we compare the difference to the first RDTSC. And if it's below a certain threshold, we then check what was the previous VMExit. So if the previous VMExit was also for an RDTSC instruction, we can just return a random number that's between 25 and 35, how long it usually takes, and then just add that to our fake RDTSC. And then we just set the correct registers, and we can return. And the important thing is with the RDTSC threshold, what if someone adds a sleep for 1,000 milliseconds, so 1 second in between there, and we just increment by 20 or 35, something in between. Then it would seem like there was no sleep. So that's the important thing about the threshold. And you can do the same thing or a similar thing for CPU ID. So you can check if there's a VMExit for CPU ID, and then you can basically just execute it normally. And for example, there's a flag that detects if a hypervisor is present, and it's set automatically by the CPU. But a program can just check that if it's running under a hypervisor. And what we can do, we can execute the real CPU ID, and then just toggle the flag. Just remove it, and then return it again. And the guest will not know that this was ever set. And yeah, here the same, we can just return 0, 2. And the same for a model-specific register. We can also, again, just get the vCPU and the registers and modify the registers there. So it's really powerful, and you can do a lot of things with it. So let's take a look at some other things that I think are really cool about this project. So for some structures, you need to allocate contiguous, so memory that's in one area, not split into multiple chunks, contiguous physical memory. And the example for that is the MSR bitmap. But most of the times, you only need virtual memory. So if you have a global allocator, you need to find a way to now allocate contiguous physical memory. You could do it on your own, but I found a really neat solution. We can just create a new struct, which is called physical allocator, and then we can implement the allocator trait for that. And if you want to take a look at the implementation, you can check out my repository. I'll publish it after this talk. And we just have to implement the allocate and deallocate function. And once we did that, we can just use the new in functions of all the structs in the alloc trait, and we can specify the allocator. So now our instance is actually allocated with physical memory instead of virtual memory. And you can even patch errors, because often if the system is out of memory, you don't want to just crash and stop. You want to handle the memory and free some memory or do some other tricky stuff. So you can actually handle it, which is really cool. And with a virtual memory allocator, this is just a recap, but I think it's also important to mention. I created a crate, which is called kernel alloc, and you just need those 3 lines and you have a virtual memory allocator. So you don't need to go through the new in and creating your own allocator. You can just use this crate, which is also really cool in my opinion. So another thing I found really useful was bit fields. So for example, in this case, we want certain fields of this struct called event injections to be a certain size. So the vector field should only go from bit 0 to bit 7, then the type from 8 to 10, and the error code valid should only be bit 11. And with this bit field crate, we can essentially do that, and it will automatically generate those functions, which is really useful. No more and or bit magic trickery. And another thing are bit flags. So this is really important because the AMD manual says how they have to be defined. And I didn't want to just create tons of constants that define those. You can actually, with this crate, define them as a struct, which is also really cool. So in this case, the enable LBR is the 0th bit, and the virtualize VM save is the 1st bit set, and so on. And one thing that really annoyed me, I had a ton of errors just because of misaligned structs or because they had the wrong size, because I used the wrong data type. And unfortunately, Rust doesn't have compile time assertions. But I found a really useful crate called static assertions. And with that, you can just use the const assert equals macro, then specify the size of and the type, and then the size of the struct. It really saved me a ton of time. So how can you actually use my hypervisor? And I think I already went over that, yeah. So I already took that away. So this was the example with the RDTSC and yeah, implementing the handlers. Yeah. So of course, I encountered some problems because it's just, yeah, it's really low level and there's not as much information available about it. So it's inevitable. So one issue was alignment. So the AMD manual is really strict. And for example, the nested page table has to be 4 kilobyte aligned. And if you don't follow that rule, bad things will happen. And yeah, it's not even gonna crash. It's gonna do weird things and you have a really hard time to figure out what went wrong. And the solution for that is to just use assertions with the static assertions crate I mentioned, and also found this align crate, which made it easier to make sure the structs are aligned. Another thing is the invalid struct sizes, and yeah, it's very easy to get the wrong data type, especially if you copy C++ code because there's these weird data types, and yeah. And unfortunately, there's also no automatic generator for all the structs from the AMD manual. There's one for C++ that just passes the Intel manual and then updates all the offsets and fields. I would have wished something similar existed for Rust with AMD, but unfortunately doesn't. And I tried to do it, implement it on my own, but parsing PDF is really no fun. I can't recommend it. But yeah, the manual solution for that again is assertions. And also had one really, really weird bug. So I didn't use the allocator I showed you before. I used my own struct. And it's called allocated memory. And it had two functions, alloc normal, so normal virtual memory, and alloc contiguous, which allocates physical memory. And the weird thing is, if we have a struct foo and we embed another instance of this allocated memory inside foo, and it goes out of scope, it just leaks memory. And it's really weird. I wrote a blog post about it, have a read. And if you know why it's happening, feel free to message me. Yeah, I solved it by just using the allocator and coming back to the box and back. Because as it turns out, box doesn't have a drop function. So if you take a look at the drop function of box, it just says it's implemented by the compiler. And I figured there has to be a reason why it's implemented in the compiler, not in the Rust code. So I just stuck with it. And hypervisor debugging is also really painful. If you have an error, it slows down the system. There's also sometimes no and really bad errors. For example, if you have a misaligned struct or a wrong value at some field, you just get a VM exit invalid. It just doesn't tell you where the error is. It just tells you VM exit invalid. Have fun, figure it out yourself. So you have to be prepared to spend a lot of time in WinDebug. The support is really good there, also for Rust, which was really surprising, but you have to be prepared for that. And there's gonna be lots of headbanging, because if you have a bug in the VM exit handler, it causes the system to freeze, and so you don't want to develop it on your main system. So you need a virtual machine, and then you need to set up nested paging and also nested virtualization. And ideally, you want to automate it, because trust me, you're gonna need to restart the VM a lot. And also performance can be a problem, because if you have lots of VM exits, it's bad for performance. And if you have a slow VM exit handler, it's even worse for performance. And if you combine those two, if you have lots of VM exits and a slow VM exit handler, it's terrible. And also, there's really a lack of resources. There's a few really good blog posts, but most of them, almost all of them, were for Intel. And there's also mostly just projects on GitHub. And I created a list on my GitHub. Feel free to check it out. And this helped me the most. And for the documentation, I just recommend sticking with the Intel or AMD manual, because they're up to date and yeah, have all the information you need. And also a really important tip is maybe just ask someone who already has done something similar, because there's a high chance they had a similar error or know someone who had a similar error, and it will save you a lot of time. And to come to the conclusion, I really enjoyed using Rust. Despite all of the problems, I still think the compiler has saved me from a lot of issues I would have had if I had, for example, used C++. Maybe I wouldn't even have finished it. And also found a ton of useful NoSTD crate. For example, I also implemented some function hooking, and it turns out the iced crate also has NoSTD support. It was really useful. I didn't want to implement my own disassembler in a Windows kernel module. And yeah, as I mentioned, the bit flag and bit field crate were also really nice. And yeah, also custom allocators. They're so powerful. And also being implemented into the alloc crate saved me a ton of time. And inline and global assembly were also really cool. And that's it. Thanks for your attention, and I'm happy to answer any questions.
Wow, thank you very much. Thank you for this interesting talk. I am It's hard for me to ask now a question because I'm a little bit overwhelmed. This is something where I haven't done any work at all. So if anyone of the in the audience has detailed questions, then please ask. Otherwise, I am going to ask questions where I would like to apologize at the beginning that maybe or probably they are very stupid. First, why? What was your motivation? Why did you do it? Did you with your custom hypervisor? Did you do something? Did you want to I don't know hack a game or was it just a learning project? I would be really interested in what your motivations were in starting this project.
Yeah, so basically, like a year ago, I already wrote my Rust kernel driver and also presented it. And also with the hypervisor, I already knew I wanted to write it in Rust.
Okay.
And the idea behind it was to have a hypervisor and then track what the entity is doing. So if they're accessing certain memory or calling a function, and then just keep track of that. And yeah, because the anti-cheat modules are usually obfuscated and you can't just look at the code or disassembly of those. So having the runtime log would be really useful. But unfortunately, as it turns out, AMD doesn't really have a lot of like analysis features. And I basically stopped the project, but yeah.
Okay, got it. Did I understand that correctly? In your research for this project, you found that companies like AMD do not support or not publish a lot of Rust-related content, right?
There's basically no Rust content.
Okay. Have you heard about anything that Rust is used more, or that they're going to that they are going to publish more Rust-related content, or do you think they will continue to rely on the whole C++ area?
That's a tricky question. I have not really heard about Intel or AMD using Rust. And I mean, the manual is like language agnostic. They don't really have C++ code examples there.
Okay.
Mostly just pseudocode. But yeah, I haven't just heard that they're using Rust.
Okay. Yeah, super interesting. I bet there are some people in the Rust community who work in a similar field in near kernel level or virtualization and so on. And I bet they are very interested in your code, which brings me to my next question. Where will they be able to find your code? I think you mentioned a blog, right?
Yep. So yeah, my GitHub username is just not minus Matthias.
Yeah.
Like the name here. And yeah, I'll publish the code after this talk and you can find it on my profile. I'll just pin it there. And there you'll also find my blog. And yeah.
Okay, very good. That is nice. I just saw it. I just have it here. Yeah, I just found it. So I hope it's okay for you if I put this one in the YouTube chat. So we have it directly here, and all our viewers can just click on the link. And I think this is your GitHub account, right?
Yep.
And there we can also find a link to your blog. So for those of you who work in a similar area as the thing that Matthias now described, I think his blog will be a super useful resource. I also have published already, while you were talking, the stars list regarding the hypervisor. So also if you are looking at it and if you're watching through YouTube, you could just use this link, click on it, and that's fine. Matthias, I think you are also a member of our Discord server, right? So if somebody has in-depth questions, you should be reachable via Discord server, right?
Yes, I'll answer all the questions.
Sounds great. Matthias, you have established your role as our Windows kernel developer with Rust guy. Second time. First one was writing a kernel driver in Rust, I think. And now we had virtualizer, a hypervisor, and I'm wondering what will come next. I'm really wondering what will come next. Do you already have future projects in planning?
I mean, I've written an UFI module in Rust. Maybe that's a potential talk. So we're going even lower.
Oh yeah, I see. Okay, so whenever you have another project like that, you are always welcome presenting it here at Rust Linz.
Awesome.
Okay, thank you very much, Matthias. We enjoyed looking at the talk, looking at your talk. And with that, I think we can switch to our second talk. Thank you very much. Thank you for visiting us. And you are very much invited to hang around a little bit here or later on in Discord server. Have a nice day. Have a nice evening. Thank you, Matthias.
Thanks. You do. Bye.
Bye. And that brings us to our next speaker, Diemo. Hi, Diemo. Stefan
Hello.
is also here. Stefan, would you like to join us for a second? Here you are. Hi, Stefan.
Hi, here I am. So just passing by. I don't disturb anybody.
Was that an awesome talk? The first talk? I mean, I need a little bit time to process that, to take a look at all these crates, because this is far away from my daily work, but I find it super, super interesting. What do you think?
Yeah, same here. So one thing that will happen is that we cut and polish this video and put it up on our YouTube channel, on the official Rust YouTube channel. So you and everybody else has the possibility to digest it again on their own and at their own speed. I guess this might be useful. And yeah, so I same here. So I know very little about it. I know a couple of things conceptually. Seeing it so hands-on and with so many examples, I need to digest it as well. But hey, I love that stuff. So I'm a huge fan of seeing things like that, and expanding my horizon a bit, because I've done websites most of my career, so I really enjoy going deeper there.
Very nice, very nice. And now we have a very different topic, don't we, Diemo?
Yes, I hope I can provide a little contrast to that very deep dive into Rust. So we are scratching a little bit on the surface from visualization, some stuff with game engines, and something more where you can see something moving or something developing. And I think it's just a nice contrast to the other talk.
Very nice. I'm really looking forward to this session, because I know Nanu a little bit. I know processing quite well, and P5.js and Phaser.io and things like that. And I haven't had the time to look at Bevy, and I'm really looking forward to it very much. So, Diemo, are you ready to go? Do you want to share your screen so we can make sure that screen sharing works properly?
Yes, I will activate it. Just wait a second. And so.
Nice. Let me put it up here. And here we are. Very good. Diemo, are you ready to get started?
Yes, I'm ready.
Very nice. So the stage is yours. We are listening. We are looking forward to your talk.
Okay. So then, hello again from me. My name is Diemo Heuer. I'm a software developer from Northeast Germany. I'm streaming from a little village near Rostock, and I'm working for a company doing some software development stuff, consulting stuff, and they are called Alto Digital Innovation, and we do also some kind of community work, like Stefan already introduced me a little bit. So thanks there for the nice words and the possibility to be here and talk a little bit about one topic I really like to talk about. And these are, let's move this away. Okay. And about cellular automata and why I think it's interesting and so on. I will tell you in this talk. At the beginning, probably in the first half, I will speak about the theory background. We are speaking a little bit about simulation. What is a cellular automata? And later, we will talk a little bit about the BV game engine. How did I find it? How did I choose it? And later, a little bit into software architecture. And in the second half, we will have a look at some code I wrote for one cellular automaton. And probably if we have time left at the end, I prepared some project I did during my apprenticeship, also related to cellular automatas. So let's start. Why cellular automatas, or what is a cellular automaton? So it has a very simple definition, and it goes something like this, that you have a discrete space, which is defined. Let's think of a 2D matrix with cells or with fields. And I already mentioned it, you have cells. And this discrete space is divided into cells. And these cells have a state. And they probably know or in relation to the environment to the neighbor cells, which also provides a state. And now, when the whole world, the whole cellular automaton will develop into the next stage of its timeline, the state of the cells will develop depending on the states of the neighboring cells. And yes, that's it. So why is it interesting? You see it a little bit here because we have a grid. There is something moving. I will tell you a little bit about it just in the next slide. But what I really like about it, it was one of my first programming projects during my apprenticeship. And you have a lot of stuff to think about. You have to think a little about software architecture, how to structure your code. You will probably do a lot of performance optimizations so that it runs smoothly, because now we got to the next point for the visualization. And it's always motivating if you see something related to the code you are writing, and even if it's almost feels like it's some kind of alive, and it's only a very simple rule set behind it, or a very simple model for the visualization, like a cellular automata where you have the cells with the states. And so you are in a good loop to have good requirements for what you're doing, but it's not always the case in the free world when you are working on your work projects, for example. Well, it's a little bit chaotic. So yes, you have some simple rules, and you can just program it, and you can extend it, and you see that something is moving, and probably not in that way you want, but you learn a lot about programming. So I think it's a good exercise, even if you are good at programming, to make something like that, or if you start with programming and do something in that kind of a simple simulation. And so let's have a look at different automatas. The most iconic one is probably the Conway's Game of Life. And automaton doesn't only stand for itself to just, you have a little rule set, and then something is happening and blinking in a way of art. It should sometimes simulate a complex aspect in a more simple way. And what Conway's Game of Life wanted to achieve is that we have simulation about biology. So we have the cells in a world, and the cells can have two states. One is it's alive, one it's dead. So cells can be born if there are enough living cells surrounding it, but not too much. Living cells will survive at a sweet spot if there are not too much neighbors, so there's probably a food problem, or there aren't too less neighbors, so there's a problem for the social environment. So the cell will wither away because of loneliness. And that's a very interesting approach of making a very complex topic very simple. And I've done this simulation at my homework back in the days, and I did a lot of extra features, and I have written it in Delphi. I can show it at the end if you want to have a look at it. Then there are some other simulations, like WireWorld, to simulate the flow of currency, of power. The Vator simulation, it's a little bit out of layout, is again a biology simulation where we have the green cells, which are fish, with the blue cells, which are sharks, and the sharks are the predators. The green fishes are the prey. The black is just empty space in a vast water planet, for example. And what the purpose of the simulation of the cellular automaton is to provide a simplification of the relation of predator and prey. And just a word of advice, it's a little bit flashy when I click here. And we see, if you look closely, we see that the blue dots are hunting the green areas. So the sharks will try to eat the fish, so they will stay alive because they have to eat. And yes, probably it's a little bit difficult to see, but here at the bottom of that little video, you have some kind of graph which is moving like a wave, and it shows if there are a lot of prey and less predators. So there will be more predators because there's a lot of prey to hunt, and the population will grow, and this will decrease the population of the prey. And so there's not enough prey, so the sharks will die from hunger. And so it's again a really complex aspect of the nature, very simplified with some simple rules and an automaton, and it just makes fun to look at something like this. I just put it on again so we can have a look at it again. So sometimes you really can get lost in that kind of simulations. Okay. And what I want to talk about is Wolfram's one-dimensional universe. I will introduce that cellular automaton when we come to the demonstration. So yes, stay excited. Okay, and then I got a plan. I did some lazy Googling what to do for my homework for simulation, and simulation programming you will find Conrad's Game of Life. And I did it back in the days with some dirty spaghetti Delphi front-end programming. And I did it again for the Rust Meetup Rostock with the BV game engine, because I always wanted to do something with a game engine. And now we will go out of the slides, and I just wanted to have a look. I just wanted to find something I could use for that simulation. And probably you know that there are a lot of RV placeholder yet in the Rust ecosystem, and these are pretty amazing websites where you can have curated lists of different crates, especially for this. Are we game yet? There's other stuff like, are we async yet? Yes, now we are async. And are we network yet? Are we web yet? And so on. And these are amazing sites if you want to probably look for a crate for a special purpose. And it's much more convenient. The sites like using crates.io. So, and some flavor text getting started. And here is some kind of some sorting happening. And if you're looking for something in the field of audio and game stuff, you will probably browse here. If you look for something for virtual reality, you will look here. And game engines, 2D, 3D, sounds fine for me. So I had a look at it. I tried different game engines out. I tried to go with Amethyst, but I didn't like the flow of programming. It felt like I had to do too much. I went for Piston. Is it Piston? It's a little bit down here somewhere. Piston here, yes. And another statistic I check if there are a lot of downloads, and this is some kind of nice versioning. And so I tried different stuff out, and I checked the crates.io page for, where is BV? Here's BV. And just check, okay, does it have a nice landing page? Because it's having a nice landing page and a good documentation. So these are good signs that it's beginner friendly, and I like to use crates with a good tutorial or with good docs, and I really enjoy it. And so I looked, okay, it's still living, it's providing new versions. And the next stuff I check is the GitHub repository. We don't look into the docs. The docs are also fantastic for BV. And I will check the examples ordner. For the guys and girls of you who didn't know this this directory in the Rust project file structure. It's a folder which holds example code for different aspects. And this is really, really helpful if you want to delve into different crates. And for me, which learns more in a practical way, it's much more helpful than reading documentation. So I have some examples here I can have a look at, for example, for Android, because BV is cross-platform, or for iOS, or for scene handling, WebAssembly stuff, and so on. Even how games will work at all. So we get an impression from Breakout example, for example. Okay, that's just this little excursus to how I deal with finding new crates which probably provide my purpose of what I want to do. And yeah, some hot facts about the BV game engine. The website also looks very nice, had a really good getting started stuff. So that's the upside of that stuff. So I've chosen my simulation, I've chosen my model, I even have a game engine, and I have the language, Rust, where I want to do it. And so let's talk a little about software architecture. So a lot of game engines are using a specific software pattern called the entity component system, or are entity component systems. And it's quite simple because it only consists of a few main components. We have the entity, which only has a unique ID. So no features for progressing some transition or something like that. Only one ID. Then to give this identity more, this entity more identity and more information it's related to, it will be extended with components, which holds data from one aspect. One aspect could be for translation. For example, if I'm moving, for example, this pen, there will be a component holding the information about the position. If it's moving, it will hold information about velocity, and it probably another component will hold information, the data about the shape, and so on. And okay, great. Now we have an entity with an identity which is unique for the whole game environment where I'm at. But now there's something to happen with it. And these four are the systems. The systems run on components. So there's a system running only for the translation. There's a system only running for probably for if the shape or the color is progressing, or if you think of more complex games, there will be systems for health, for mana, for the daytime, for if you play survival games, for the handling of thirst and hunger, and so on. And it always runs, and it's a game loop. And to get a little bit more special in that way, we have a look at a little example. We have here the entity with different components docked to that entity. And like in my little example, we have some data on that components, like x coordinates, the acceleration, and then, so that's my main object I'm looking at the moment. And we have the game loop, and there are a lot of systems. Think of systems in some kind of functions, of methods. We will have a look at it at the demonstration. And there's a system for handling the gravity. And the gravity will have a look at all the entities and will check it. Hey, are you having the gravity component? Okay, great. I will do something with it. And so it gets the gravity, the entity, and does something with the gravity to calculate the new position. And then the next system will do something, and so on. We have an infinite game loop. Good. And now we are at this point where we are almost at the demonstration. Before I forget it, I want just to mention some sources. Like I will provide a repository with the code. I will just post it at YouTube stream in the chat if you want to follow during my talk further into the code. And I just linked some, I think, pretty good sites to get into entity component systems, or into the BV game engine, or into cellular automata as well, or which is a really great source of inspiration and knowledge transmission, is subreddit for cellular automata on Reddit. Okay, then give me some seconds and I will post this into the chat. Okay. I hope I made it public, so otherwise I will just make it shortly after this talk. And now we will have again a little theory about probably most of the most simplest cellular automatons, the Wolfram's one-dimensional universe. And if you think of the natural world we are living in, it's 3D and probably much more complex with time and stuff like this. So we are not thinking in a 3D room. Of course, a cellular automaton could be 3D, but not this one. So we don't have volume. It's not in the 2D room, so we don't have an area. We have the 1D room, and it's think of a line, just for a little presentation. Let's imagine this is a line, and we have cells, and the cells don't really have space or area. They are just knowing which its neighbors are on this line. And it's not only a line with defined end and beginning, it's some kind of ring. So it's infinite and closed in itself. And every cell inside this universe has a state. And if you have a look at something like this, you'll probably see, okay, I now see here something 2D. But in reality, it's the universe is only one line. And what we see here is the progression of the universe through time. So every new line is the next step in the timeline of that universe. And we see here probably the Big Bang started small. There's a special rule set for that universe, and the universe will expand, and we see a structure. We will see the textures, and we will see that it will develop or evolve in a special way. And so the rule set is that we have, if we have a look at here, I will explain what the bit pattern means shortly in some seconds. We have our cell here, and the next state of the cell provided in the timeline depends on the state from the cell itself, from the neighboring states, from the left and from the right cell. And what we see here is, okay, if the 3 cells are full, the next, or the main cell and the left and right neighbor, the next cell will be empty, and it's recognized with a 0 at this point. For this stuff, every cell is empty, and the next in the timeline will be 0 as well. For this case, the left neighbor is empty, the cell itself and its right neighbor is filled, so the next state will be filled, and it's related to a 1. And probably you already counted the digits, and it's 8. So we have 1 byte, 8 bits. And in Wolfram's, if you talk about Wolfram's universe and talk about different rule sets for this, because we have 4 cells, there are we have this kind of combinations for the next state. And so if we want to apply a simple rule, we will speak about, we apply rule 1. We will apply rule 42. We will apply rule 182, and so on. And there are, in these 256 possible combinations, there are a handful of interesting developments. Here we see the different bit combinations, and this will make different structures of the universe, how it will evolve from a single filled cell at the beginning. So that's the theory. And now we will have a look just what is happening in my little application. And we see, okay, here's something going on. We are going through the timeline and we see different structures. We see that some triangles will evolve during the universe. So, but it's not something we saw before. But I programmed something. If I start with a single cell, we see a pattern which will match to. Let me have a look, and it's that pattern, rule 182. And it's quite amazing to make that kind of structures in a procedural way. Okay, and now to the code. So now you should see my Visual Studio Code, and everything starts with the main function. Because of things I've learned during my other projects, I wanted to make it a little bit more structured. And so I begin everything with some kind of configuration. And from this basic configuration, the first universe state will be developed. I will initialize the control state. I will initialize the state of the UI to have the stuff to begin with for a default configuration. Then we have some BV related stuff. We see here, probably you know this kind of method chaining. It's some kind of builder pattern where you prepare your application with stuff you want to have inside with different functions. And at the end, there will be a run and everything will start. Now, at the beginning, I'm going to add some default plugins because BV has a plugin system inside of it. So we see here there's some plugins for logging, for time management, for input management, for window management, and so on. So it's a good foundation to start the program. Then I want to provide some resources. Think of resources in this gaming environment as some kind of singletons. There can only be one instance, or there is only one instance I can easily access. I only need one configuration. I only need one state of UI and one state of the universe, because there is only one universe in my simulation. Then after I prepared all the resources I have, then the systems will kick in. At the beginning, I will define a special system, a startup system, to make some basic setup. And after everything is set up, I add other systems, which now are in the game loop and will just be executed whenever, as fast as often as possible, and not in an organized order. I can achieve it if I link the different systems to each other, but I just left it free at this point. So I have one system handling the resizing of the UI. So if this stuff is changing, so the size of the cells will change. Then I have some systems for keyboard input. I have one system for iterating the universe. So here's some iteration happening. Then I have a system for visualization, because when the universe is iterating, then it needs to be visualized. And at the end, there's just some convenience system where it's made for examples and prototyping. If I press escape, the application will close. Now let's have a look at the different systems. Word of warning: you will see just got a little settled because I had some stuff. I hope the The hardware is still working. Okay, so we begin with the setup system. And yes, a word of warnings, macros. BV is using a lot of macros, and with that macros, this heavy use of macros, it's providing a very, in my opinion, lean developer experience. And so if you're asking where I'm calling the setup and putting the commands inside, I'm not doing it. It's some kind of the macro magic in the BV background. And so I can just name or classify a function as a system. And because BV knows it's a system, because it's named here, I can provide different arguments. For the setup is simple. The commands are something where I can interact with the game engine. I want to start to spawn or to prepare everything for a 2D camera. So for the keyboard input system, it's more complex. I have the commands because I want to react to the keyboard inputs. I access my resources, which are fixed, like the configuration, or from the default BV plugins, the input system provides me here the key pressed in that manner. Then I have the control state, the UI state, and because probably something will happen for the control state and UI state. And so it's mutable in that. And now here we have something related to the software architecture of entity component systems. I have a query where I can demand all entities which have the component cell, and then I can work with them. And then, yeah, some stuff is happening for the keys. Here I have some for my resize notification for resizing the window. And I'm doing it in a very not performant way because I'm just despawning everything. There are better options. From time to time, I'm optimizing this little example. So it's getting better. Then I have my iterate universe, which is just calling on that universe state, which is an automaton. So iterate and it will work on itself. And then probably for the last stuff, we have the that I want to update the visualization. And I did some optimization. In my opinion, I'm only scratching at the surface of the BV game engine. So I only visualize or draw new cells if it is necessary. And I only draw the timelines which are necessary. And then it gets through everything, gets the positions. And yeah, the more interesting part is now here when we go to the sprite bundle. And the sprite bundle spawns a basic entity with the components for the visualization, where we have where is it on my screen, which color does it have, and so on. And with the commands, I will not only spawn the bundle for the representation, I want also to add the component for the cell so that my game object, my entity, has these informations. And so I'm spawning the bundle, and now here I can do again with method chaining, build more and more components to bind more and more components to my entity. It's not really necessary for my processing at the moment, but it helped me for some debugging reasons at this moment. Okay, and then we have just a last helper function where I can get my stuff. And generally, I separated my code mainly in two parts. So the automata is completely independent from the UI. So if I want later to make another presentation, because to be honest, it's fun to play around with BV and a gaming engine for this kind of stuff. But if you want a really efficient way, you probably would go for some OpenGL stuff or for drawing directly. And so you have an entity system, a component system has very less overhead, but with that kind of presentation, you have even less overhead. So, and because we have some minutes, I just want to show you some of my stuff I did during my apprenticeship. And yes, this is some application written in Delphi for Conway's Game of Life. And this is just some prepared stuff. I can draw here if I want, but I don't want it at the moment. And just set hi. And if I press start, the system will start to develop. And I made some check that it recognized, okay, the world stagnated. It's not moving anymore because these are stable figures in Conway's universe. I prepared some stuff like this. Okay. So I will generate. This is now random. Green is alive, black is dead. And now I will just press start. And you will see there's some movement, some kind of stuff is evolving. Some figures will be there. There will be some flickering figures like this. And one thing you saw at the beginning of my slides was a glider, just an object which moves infinite. And I provided some nice stuff like, or some extra stuff like, what is if the borders are considered as being alive? So we, I think I have to reset, and then we have something like this because we have an endless source of living borders providing some stuff. And you can have a very complex, not very complex, you can have a very simple rule set for that kind of stuff, and you can achieve amazing outcomes. So for example, you can use it for generating some kind of mazes. So if I start here, you will say you don't have the flickering anymore. You have something growing like a sponge shroom, or I don't know, something like that. So it's not really a maze, but it probably almost looks like it, and it grows. And one of my favorite worlds is the copy world, where we start with something. I've printed it in preparation, and then it looks chaotic. It gets into new forms, and at some point we see it copies from the center. And if we go further and further, and it's more chaotic, again, we have the faces, which were one step before some chaos like this. And with the rule set, bam, a lot of happy elves. Okay, and there's a lot of stuff going on, just as the last stuff. Here's a blinking world, which you can use probably for terrain generation or something like this. There's with the rule set, it will stabilize in some areas. Let's call it this. And if you then keep running or developing, it just start blinking. Okay, and with the last slide from my presentation, it's here, and here. Just one stuff from the subreddit of Cellular Automaton from Reddit. Here's some piece of Cellular Automaton art called The Mountain. Yes, and then I'm finished.
Very nice. Thank you very much for this interesting talk. Oh, I love this automata art. I didn't know that, and it looks beautiful.
There's a little scene for it.
Oh, really?
A little scene for everything. I think, yes, there are some pieces of art, and they're trying to get, for example, this stuff in the middle. It's some typical, some typical Wolfram Universe rule set. These rule sets are from other automatons, and so on. And they're putting everything together and make some pieces of art. Probably, I think Lisa would like something like this as well.
Absolutely. That brings me to an absolute crazy idea. Never thought of that, but that would be a crazy project. Have you ever heard of the programming language Piet? Piet?
No.
Heard of
No.
that? Oh, you should
No.
take a look at it. Piet is an esoteric programming language, and essentially you program it using pixels in images. So certain changes from one pixel to the other in the color has a certain meaning, has certain commands. So you can draw a picture, and it's also a kind of scene where you can draw a picture that looks beautiful but is really a program. And it would be super interesting if you could build an automata that generates a program that can be integrated with Pete. So that would be really, really interesting. That would be a crazy idea. I've never thought about that. But back to your talk. Yeah, thank you very much. I see that some people, Wolfgang, was very happy because he saw Delphi in a Rust meetup. So thank you for that. I also like that you covered this topic because I don't know if you know that I'm a part-time teacher. And you have probably heard about the Coder Dojo, and doing such automatas is really a great way of exercising, doing some algorithmic exercises, software architecture exercises, and so on. So yeah, I think this is really, especially for beginners, that is a very valuable lesson that you just showed us. Absolutely.
And it's good if you're, like I said, in your daily work, and you have some nice project like this, and it's good, and you will learn a lot of it, especially if you try to use different programming languages with different paradigms, like functional versus object-oriented. And I had a lot of pain programming my first automaton in Rust, because I wasn't able to program in that way like I did in C#, for example.
Yeah, absolutely. I fully understand what you mean. And in Rust trainings, for instance, also in other programming languages where I am a teacher or a coach for professional programmers, so many ask me, hey, can you tell me a book? I would like to learn Rust. And I always tell people, it's not about books. It's not about reading things. It's about doing things. And sometimes people simply don't have ideas with what they could get started, because maybe they don't have a project in work, but they still want to learn Rust. So what should I do? And programs like the one you showed us are exactly the right way to get started. They are well documented. There is a scene, there is a community for it. You can ask people, and you can go beyond the craziest ideas by extending these solutions as far as you want. Absolutely. I'm also very interested in this Bevy, in this Bevy game engine. Did you try other game engines too, other Rust game engines? I think you mentioned some of them when you showed us the RE Game Yet site, right?
Yes. So let's have a look at it again. It's here, and I
By the
think
way, people liked your talk, as you see. We got a comment. Amazing.
Yeah, great. Happy you liked it, because I think some people probably get bored already, because I really like to speak about this this topic all the time, and yeah. So nice that you liked it. And yes, I started with MSysT because it was one of the most popular game engines. It has a good good documentation. It has a lot of examples. In my opinion, I had some struggles to get into the flow of programming with that kind of stuff, and I'm not sure at the moment. I don't want to tell something wrong, but it seems like that the MSysT project for itself was struggling a little bit about what to do, because they spent a lot of time to program their own entity component system called Legion, which is pretty good as well. If you only want an entity component system, check out Legion from the MSysT team.
Okay,
I think. And yeah, so it was a little bit too heavy for me, to be honest. And then I tried Piston.
Okay.
And I think Piston probably is a game engine which just has some bindings in Rust, and the core is in another language.
Okay.
So it's so there's a very big community around Piston, And you see it from the downloads here. It has the most downloads of all, I think, on this site. So I tried this one out. And I programmed this Wolfram universe as well with it. But only after I did it with BV, because I've trying BV out since I think 3 or 4 major versions. So the version behind the first 0. Let's say about that way. And BV had a nicer flow for me for programming, and Piston doesn't felt so developer friendly for me. I could achieve what I wanted to achieve, but the BV engine felt more rewarding and supporting.
Okay.
And another part for the BV engine is completely written in Rust. And that's another aspect I like about this. So
I definitely have to check that out. I read recently some articles about BV, and it looked really nice. And your talk was another pointer to this framework. So I should really give it a try. Thank you very much for that.
And they polished their API a lot during the last releases. So it's a much better experience than a year or 2 years ago, or 1.5 years. I don't know, but it's on a good way. It's fun to program with.
Okay, very nice, very nice. Hans-Peter told us he's a friend from the Coder Dojo, and you can compile it to web with Bevy. So this was his comment. So it seems that it's possible to use WebAssembly with Bevy too, right?
Yes, I did it already. I made some example stuff with the U engine for building a single page application, and then integrating the this WebAssembly. Yes, I tried out a lot of stuff with Rust beside my working stuff, where I built mainly APIs or something like that. So yes, it's possible. So if you want to try out some single page application stuff with Rust, check out the U engine, YEW.
Yeah.
And it's the most popular one. And I had also a lot of fun with the Dioxus engine. It felt nice as well.
Okay. Thank you very much. Thank you for sharing that. Okay, very nice. Diemo, unfortunately, your chat message wasn't published. I don't know why. Maybe you can either try it again or post it on our Discord server, or send me the link and I will post it on the Discord server, just as you prefer, because it would really be nice if all the people see the material that you brought together, if somebody would like to check that out.
Yeah.
You just posted it in the private chat, right?
Yes. Right.
Okay, so I'll copy it and put it into the comment. Yeah, okay. Somebody already. Stefan. Stefan is here.
It was me.
Yes.
Okay.
The magic in the background, the magical hands.
the link poster. Yeah.
Yeah, Timo, thank you very much. We especially loved the exchange with the Rust Meetup Rostock. Stefan already visited you. I think we have an appointment somewhere at the end of this year. Maybe I have a chance to do a talk at your meetup too. That would be really awesome. And thank you very much for contributing one talk to our meetup. And I'm pretty sure we will find additional opportunities for exchanging talks or ideas in the future.
Yes, thank you for your invitation. Would be happy to be here again.
Thank you. Thank you, Diemo. I wish you a nice evening. Thank you and goodbye. See you next time. Bye.
Bye.
Stefan, a nice mixture today, right? Deep into hypervisors and then learning Rust with Bevy and automatas. I enjoyed it. I really enjoyed it. The first one brought me out of my comfort zone, and the last one brought me into my comfort zone again. But I've never tried these things with Rust, so it was super interesting.
Cool.
Yeah,
great. Very good. Yeah, so I guess it shows the versatility of the language, doesn't it? So to be able to work on both ends of the spectrum, that's quite nice, actually.
Absolutely, and that is the awesome thing with Rust. That's the really important stuff. You are not limited to systems programming. You can do systems programming, but you can also use it for application development. So I really think that this is a nice thing with Rust, and that many other programming languages can't fulfill in that. We have one last thing to announce at the end. I think that would be a nice closing. We can announce the next Rust Linz meetup. It will be on the 27th of November. So please save the date. We already have one very exciting talk. We will have a talk about embedded Rust on the ESP32 from Uri. He will visit us from Espressive Systems. So that will be a very interesting one. And we also are in the last coordination sessions with our second speaker. We will announce the second speaker shortly. So in approximately 1 month, be back, and we will have our next Rust meetup again with some deep dive embedded stuff and a second talk that I'm really looking forward to.
Yeah, I'm looking forward to that.
Very good. So with that, everybody, thank you for watching. Have a nice evening and come back in November.
Bye.
See you. Bye.